So far, Dyson's equation is exact, providing that we take into account all possible diagrams in the proper self-energy. The difficulty is, of course, that we have in principle an infinite number of diagrams for the proper self-energy. So we need an approximation, and the mean field approximation is obtained by only keeping the lowest order Feynman diagram. Because there is only one vertex, the interaction occurs only at a single point of space-time, and that's why we have a delta function both in time and in space. Feynman rules tell us that the value of the vertex is just g, and because the same time appear in both arguments of the propagator, we need to replace by, which we showed to be equal to the particle density in x. In the ground state, the density doesn't depend on time because the system is static. With this approximation for the proper self-energy, we can rewrite Dyson's equation. We can rearrange this equation by multiplying by omega minus h naught to the left. Let us first work out what it does to the free propagator. Note that phi I naught is eigenstate of h naught with energy ei naught. This gives us an omega minus ei naught to the numerator, which cancel with the one in the denominator. Phi I naught spans the entire single particle Hilbert space, therefore the sum over I of phi I naught is just the identity. So multiplying Dyson's equation by omega minus h naught will give us two delta functions, here and here. We now substitute the expression for the propagator as function of the single particle wave function and single particle energy in presence of interaction, which are the quantities we want to determine. We now multiply by phi j of x and we integrate over x. And we use the fact that phi I and phi j are orthogonal. We now multiply on both sides by omega minus ej plus I epsilon. Rearranging, we get the mean field equation for the single particle phi j. This is a nonlinear Schrödinger equation because the operator contains a density which itself is expressed as function of the wave function phi's. The interaction is described by a self-consistent mean field which depends on the density. And we see that this mean field is just the proper self-energy we obtained in the mean field approximation, so when we only kept the lowest order Feynman diagram for the proper self-energy. So we obtained this equation for a system of bosons with a contact interaction, which simulates, for instance, cold atoms. But the same procedure can be applied for more complicated systems, so for instance for fermions and for interactions which are not contact but finite or long range. So for instance, if you have a system of electrons interacting via the Coulomb interaction, you can similarly work out mean field equation for the electrons, and which will give you the Hartree-Fock equation in this case.